Look up at the night sky and choose a star, any star. It seems to exist right now, hanging above you at this exact moment. But that simple assumption may be completely wrong. The light entering your eyes tonight could have begun its journey before you were born. Some of it left its source before the first human civilizations appeared. And when we look far enough into the universe, we receive light that has been traveling toward us for billions of years. The object that sent it may have changed beyond recognition. In some cases, the stars that once illuminated their surroundings may already be gone. So here is the unsettling question. Have human beings ever actually seen the universe as it exists now? The answer is stranger than it first appears. We don't see the cosmos in the present. We see layers of its past, stacked across distance. The farther we look, the deeper into history we see. A light year sounds like a unit of time, but it is actually a unit of distance. The distance light travels through a vacuum in 1 year. Light moves at approximately 186,000 miles per second, or about 300,000 kilometers per second. In a single second, it could circle Earth more than 7 times. In 1 year, it travels roughly 5. 88 trillion miles. That seems unimaginably fast. And yet the universe makes light look almost painfully slow. The moon is close enough that its light reaches Earth in roughly 3 seconds. When you look at the moon, you are seeing it as it was a little over a second ago. Sunlight takes about 8 minutes and 20 seconds to reach Earth. If, in an impossible thought experiment, the sun could suddenly disappear, Earth would not visually register that event immediately. General relativity also tells us that changes in gravity do not propagate instantaneously. They travel at the speed of light. For those 8 minutes and 20 seconds, no information about that hypothetical event could reach us. Already the word now has begun to fracture. Travel farther. The nearest star system to our own, Alpha Centauri, is more than 4 light years away. Its light crosses interstellar darkness for years before reaching our telescopes. Sirius, the brightest star in Earth's night sky, is about 6 light years away. The Sirius you see tonight is the Sirius of more than 8 years ago. Betelgeuse is hundreds of light years away. When astronomers observe its enormous unstable surface, they are not watching it in real time. They are receiving ancient information carried across hundreds of years of space. This doesn't mean Betelgeuse has necessarily exploded already. Astronomers cannot simply assume that. But it reveals something more profound. Until information reaches us, we cannot know its current condition through observation. Distance creates ignorance, and light years measure the size of that ignorance. This problem fascinated generations of physicists because it is connected to one of the deepest discoveries in modern science. There appears to be a fundamental speed limit governing how quickly causal influence and information can propagate. Albert Einstein transformed our understanding of this limit with special relativity in 1905. The speed of light in a vacuum is not merely a technical number describing photons. It is woven into the structure of spacetime itself. Leonard Susskind, one of the major architects of modern theoretical physics, has spent decades thinking about what happens when the principles of relativity collide with quantum mechanics, gravity, and black holes. His work repeatedly returns us to the same disturbing theme. Information is not free to travel however it wants. The universe has rules about who can know what and when. Imagine 2 civilizations separated by 1,000 light years. Civilization A sends a message. Are you there? Even traveling at light speed, the message takes 1,000 years to arrive. Civilization B immediately replies. Another 1,000 years pass. Civilization A receives the answer 2,000 years after the original message was sent. That is not a conversation in any human sense. Entire nations could rise and fall while a single question crosses the darkness. Now increase the distance. The Milky Way is roughly 100,000 light years across. A civilization on the opposite side of our galaxy could transmit a signal today, and humanity might not receive it for tens of thousands of years, depending on the separation. Even if intelligent civilizations filled the galaxy, the speed of light would keep many of them causally isolated on human timescales. This changes the emotional meaning of the night sky. Space is not merely empty. It is delayed. Every point in the sky comes with its own timestamp. And then the distances become truly enormous. The Andromeda Galaxy is about 5 million light years away. When you observe Andromeda, the photons entering your telescope began traveling toward the Milky Way around 5 million years ago. They started their journey long before modern humans existed. You are not simply seeing another galaxy. You are seeing evidence from another geological age. Imagine an astronomer living in Andromeda with a telescope impossibly powerful enough to resolve Earth in exquisite detail. If that astronomer were looking at Earth today, they would not see our cities, airplanes, satellites, or radio towers. They would see Earth roughly 5 million years in our past. The two galaxies may exist simultaneously in some practical sense, but neither can observe the other's present. This is where relativity makes the story even stranger. In everyday life, we instinctively imagine a universal cosmic clock. We picture one enormous invisible hand sweeping across the universe, defining what is happening right now everywhere. Einstein showed that nature does not provide such a simple universal present. Observers moving relative to one another can disagree about whether distant events occurred simultaneously. This is not because their clocks are defective. It is a consequence of space-time itself. There is no absolute notion of simultaneity for spatially separated events in special relativity. The universe does not hand everyone the same cosmic now. Susskind often approaches physics by forcing ideas into extreme situations where our intuition breaks. Black holes provide perhaps the ultimate example. Imagine falling toward a black hole while another observer watches from far away. From your own perspective, if the black hole is sufficiently large and conditions are otherwise survivable, crossing the event horizon need not be marked by a locally dramatic boundary. You continue falling. But the distant observer describes the situation differently. Signals you send outward become increasingly redshifted and delayed as you approach the horizon. Your image appears to slow and fade. Two descriptions of one physical process seem radically different. Black holes therefore turn the problem of observation into something much deeper than simple travel time. They force us to ask whether information can disappear from the universe entirely. Stephen Hawking's discovery that black holes can emit thermal radiation created one of the greatest crises in theoretical physics. If a black hole forms from matter carrying detailed quantum information and then eventually evaporates into apparently featureless thermal radiation, what happens to the information describing what fell in? Ordinary quantum mechanics says information should not simply be destroyed. Yet Hawking's original calculation seemed to suggest that it could be. Susskind became one of the central figures, arguing that quantum information must ultimately be preserved. This struggle helped inspire ideas such as black hole complementarity and later contributed to the development of the holographic principle. The basic lesson is astonishing. Our everyday picture of information as something located neatly inside objects may be incomplete when gravity and quantum mechanics meet. But even without black holes, ordinary light already reveals the deeper problem. Everything you know about the external universe arrives through signals: light, particles, gravitational waves, some physical influence carrying information from one place to another. And all causal signals are constrained by relativity. You never experience a distant object exactly as it is now. You experience information that has had time to reach you. Even the person sitting across a room from you has seen a tiny fraction of a second in the past. The delay is far too small for your brain to notice, but conceptually it never disappears. Reality reaches you late. Your entire visual experience is, in that sense, a reconstruction from incoming information. The effect becomes scientifically useful when astronomers point telescopes into deep space. A telescope is not merely a machine for seeing far away. It is a machine for seeing backward in cosmic time. The Hubble Space Telescope showed humanity galaxies whose light had traveled for billions of years. The James Webb Space Telescope pushes our observations into extremely early eras of galaxy formation. Astronomers are not looking at old photographs stored somewhere in space. The photons themselves have been traveling across the expanding universe since those ancient events occurred. This gives cosmologists something almost miraculous. The universe carries its own historical record. On Earth, if we want to study ancient Rome, we rely on ruins, documents, artifacts, and archaeology. Astronomers can directly receive ancient light. When we study sufficiently distant galaxies, we are observing galaxies during earlier stages of cosmic evolution. Distance becomes history, but there is a complication. The universe is expanding. This means the relationship between distance and light travel time is not as simple as multiplying the number of years by the speed of light. While photons travel, space itself evolves. In cosmology, astronomers therefore use several different definitions of distance depending on what they are calculating. This leads to a fact that sounds impossible the first time you hear it. The observable universe is about 8 billion years old, yet the radius of the observable universe in terms of present-day proper distance is roughly 46 billion light-years. How can we observe something now tens of billions of light-years away if the universe is only 8 billion years old? Because the space between us and those distant regions expanded while the light was traveling. The photons began their journey when their sources were much closer in the cosmological sense. During billions of years of travel, the universe continued expanding, stretching the distances between unbound regions. The light also stretched. Its wavelength increased with the expansion of space, producing cosmological redshift. The farther into the cosmos we look, the more strongly this expansion becomes part of the story, and eventually we reach an ancient wall of light, the cosmic microwave background. It comes from a time roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and nuclei to combine into neutral atoms, and photons could travel freely over vast distances. Before that era, the universe was an opaque plasma to electromagnetic radiation. So when our instruments map the cosmic microwave background, they are not merely observing something extremely far away. They are seeing the oldest electromagnetic light that can reach us directly. Behind that surface lies an earlier universe that ordinary telescopes cannot see with photons. We are surrounded by an ancient image. Every direction we look deeply enough eventually leads toward the infancy of the observable cosmos. But now comes an even more unsettling idea. There are places whose light has never reached us, and there may be places whose light never will. Because the universe has a finite age, there is a limit to the region from which signals could have reached Earth since the early universe. This helps define our observable universe. But cosmic expansion introduces another boundary, the cosmic event horizon. Observations indicate that the expansion of the universe is accelerating, commonly described within the standard cosmological model by dark energy, often represented mathematically by a cosmological constant. If accelerated expansion continues indefinitely in roughly its present form, sufficiently distant regions will become permanently inaccessible to signals we send now. This does not mean those galaxies locally race through space faster than light, in violation of special relativity. General relativity allows the distance between sufficiently remote, gravitationally unbound regions to increase in ways that have no simple special relativistic velocity interpretation. The consequence is nevertheless dramatic. There are galaxies we can observe today, whose future evolution humanity may never witness indefinitely. The photons arriving now began their journeys under different cosmic conditions. Over enormous timescales, more distant galaxies beyond our gravitationally bound neighborhood will become increasingly redshifted and eventually observationally inaccessible. Imagine an astronomer in the unimaginably distant future. If civilization somehow survives for trillions of years around long-lived stars or other energy sources, the visible universe could look radically emptier than it does today. The Milky Way and Andromeda are expected to evolve into a merged system, together with other gravitationally bound members of the local group, but galaxies beyond that bound region will continue receding with cosmic expansion. Future astronomers may inherit a sky in which evidence of today's grand cosmic web is far harder to detect. That means our era may occupy a remarkable observational window. We can see enough of cosmic history to infer an expanding universe. We can detect the cosmic microwave background. We can observe enormous numbers of galaxies. The universe has allowed us to read chapters of its history that future observers may struggle to recover directly. Yet even we see only a fraction of the whole story. The observable universe is not necessarily the entire universe. It is simply the portion from which information has had the opportunity to influence us. Beyond our cosmic horizon, space may continue. How far? We do not know. It could extend vastly beyond the observable region. Depending on the global geometry and topology of the universe, it could even be spatially infinite. Current observations tell us the observable universe is very close to spatially flat on large scales, but they do not establish that the entire universe is infinite. This distinction matters. When people say the universe contains billions of galaxies, they are usually talking about what can be inferred within the observable universe. The entire cosmos could be far larger. There may be regions so distant that no message from them has reached Earth in the entire history of the universe. Not because our telescopes are insufficient, not because their stars are too faint, but because causality itself separates us. No engineering breakthrough can recover information that has not had a causal path to us. That boundary is not a technological problem. It is written into space-time. And this brings us back to Susskind. Much of modern theoretical physics is a struggle to understand what information means when horizons exist. Black hole horizons hide regions from certain observers. Cosmological horizons limit what portions of the universe can ever communicate with us. Quantum mechanics insists that information behaves according to extraordinarily strict principles. Gravity reshapes the stage on which that information moves. Some of Susskind's most influential work emerged from taking those tensions seriously. The holographic principle, developed through work by Gerard Hooft Susskind, and later sharpened in major ways through string theory and gauge-gravity duality, suggests that the information content associated with a region of space may be describable in terms of degrees of freedom associated with a lower dimensional boundary. It is one of the most surprising ideas in theoretical physics, but it must be described carefully. It does not mean that scientists have proven our everyday universe is literally a computer-generated hologram. Rather, holographic ideas provide powerful clues about quantum gravity, especially in theoretical settings involving black holes and certain space-time geometries. The deeper implication is enough. Space, gravity, information, and geometry may be connected far more intimately than ordinary experience suggests, and light years expose that connection in the simplest possible way. They remind us that information requires time to travel. That observation has another consequence for one of humanity's oldest questions. Are we alone? Suppose a technologically advanced civilization exists 10,000 light years away. If its astronomers observed Earth today, the light reaching them would show our planet 10,000 years ago. They would see no modern industrial civilization, no radio towers, no cities illuminated electrically. Meanwhile, any signal they sent during our recorded history could still be crossing the galaxy. Two civilizations could coexist for thousands of years without either knowing the other exists. Now imagine that technological civilizations are short-lived compared with galactic timescales. One civilization might disappear before its first message ever reaches another. The famous silence associated with the Fermi paradox becomes even more complicated when we remember that the galaxy is not only enormous in space, it is enormous in communication time. Intelligence might exist, signals might exist, but civilization A and civilization B must overlap not just spatially, but temporally and causally. The universe can contain possibilities that never meet. There is something almost tragic about that. Imagine humanity discovering a clear artificial signal from a world 1,000 light years away. The signal would be revolutionary, but immediately we would realize something devastating. It was sent 1,000 years ago. The civilization speaking to us would belong to our past light cone. We could answer, but our response would arrive another 1,000 years later. We might discover intelligent life and still never experience anything resembling a conversation with its original senders. A message from the stars could be both proof of companionship and evidence of cosmic isolation. Yet perhaps the strangest consequence of light years is not about aliens, galaxies, or black holes. It is about the present moment itself. You feel as though the universe exists around you right now. And locally, that intuition works beautifully. But extend now across interstellar distances, and relativity refuses to give you the simple universal present your intuition expects. What is happening on a planet 1 million light years away right now? You can choose a reference frame and assign coordinates to distant events. Physics allows precise calculations, but nature does not provide a unique, observer-independent cosmic simultaneity shared by everyone. Different observers in relative motion can construct different surfaces of simultaneity. That sounds abstract until you realize what it removes. The universe is not a stage where everything updates simultaneously for some hidden cosmic spectator. There is no known privileged observer standing outside space-time watching all events occur at once. There are events. There are observers. There are causal relationships. There are signals connecting some events to others. And there are horizons beyond which information cannot currently reach us. Every time you look at the stars, you are therefore looking into what physicists call your past light cone, the collection of events whose signals have had enough time to reach you. Your observable reality is bounded by causality, and the farther away something is, the older the version of it you can see. A star 10 years away appears 10 years younger than its current local state. A galaxy a billion light-years away is observed at an earlier stage of cosmic history. The cosmic microwave background shows a universe dramatically younger than the one surrounding us today. The night sky is not a picture. It is an archive, and every photon is a messenger that survived the journey. Some traveled through interstellar dust, some were bent by gravity, some were stretched by cosmic expansion, some crossed billions of years of evolving space before striking a telescope mirror on a small planet orbiting an ordinary star. Then, for perhaps the first time, a conscious observer asked what that photon meant. That may be the most remarkable part of the story. We are physically trapped by the speed of information, yet the same limitation gives us access to cosmic history. If light traveled infinitely fast, the sky would not provide the same direct layered view of the past. Because light takes time to move, distance becomes a record of time. The limitation becomes the telescope. The delay becomes the evidence. The universe's refusal to reveal a universal present allows us to reconstruct billions of years of its evolution. But the price is severe. We can never simply step outside spacetime and inspect the whole cosmos as it exists at one absolute moment. We receive fragments, ancient photons, gravitational waves, particle detections, redshifts, patterns in background radiation. And from those fragments, physics reconstructs a universe no human being can ever observe all at once. Perhaps that is why the light year is far more unsettling than its textbook definition suggests. It does not merely tell us how far away the stars are. It tells us how separated we are from them. It measures the delay between an event and our knowledge of that event. It reminds us that some regions may forever remain outside our reach. And it exposes something deeply counterintuitive about reality itself. When you look into the night sky tonight, almost nothing you see is exactly as it is at the moment its light reaches your eyes. The sky is filled with different paths arriving together. 8-minute-old sunlight, years-old starlight, centuries-old stellar light, millions of years-old galactic light, billions of years-old radiation from the deep universe, all arriving in the same present experience. You stand at the meeting point of countless histories, and somewhere, perhaps unimaginably far away, another observer may be doing the same thing. They could be looking toward the Milky Way, toward our sun, toward Earth. But depending on their distance, they might see a world before humans existed, a world before dinosaurs vanished, or perhaps a young solar system still forming from dust. To them, our future has not arrived. To us, their present may never arrive. And if reality only becomes knowable when information has time to reach an observer, then perhaps the most haunting question is not what exists beyond the farthest light we can see. It is how much of reality can exist forever beyond the boundary of anything we will ever be able to know.